name is Mirno from ISMA University in Russia, and he will tell us about miniaturized printable potentiometric ion selective electrodes based on carbon fiber and MXene nanoflakes for calcium detection.
Okay, cool. Thank you, Emilia. Good afternoon, ladies and gentlemen. I have very strange and very long name of my talk, but I think what is inside is a little bit more clear and more understandable than the naming. So during the pandemic time, we faced some challenges, I would say. So we need to somehow to measure some ions in blood samples of patients to help doctors, for example, with recognition of early stages of COVID disease and so on and so forth. And we had to took part in this race. We published 2 or maybe 3 papers on that topic, developing sensors for potassium, sodium, and for example for zinc ions, especially zinc one. It was done in blood and urine of a real patient, so we can prove that it's working on real samples. At the time when I arrived, I was mainly involved in the project of memristive effect for MXene, and today in the morning Hubert told a bit about that, about chematronics, ionotronics, and so on and so forth. And at that point we decided, okay, why not to combine these 2 approaches, polyelectrolytes and such sensors, with my MXene, which for what I also used polyelectrolyte matrix, so to get some synergetic effect. And why we choose calcium ions? Because calcium is very, very important for our body, for our health, because it's involved in a lot of metabolisms. For example, vitamin D, bones, phosphorus, it's all about calcium. And also some harmonic hormones pathways also is about calcium ions. Couple of words about ion selective electrodes. So, you know, I hope this equation. If we rewrite it a little bit more general form like this, so you have a membrane that separates 2 liquids. In one liquid we have some ions, in another we have lack of these ions. So we finish up with this equation, and we have very classical electrodes like this, where we have glass frit that separates to aqueous solution, or we have some modern stuff like that. Thanks for Bart for these nice pictures. And okay, we also need a membrane, even if we don't have any kind of second liquid. We still need a membrane which separates and 2 liquids or 2 liquid and solid. The only good stuff from that, we do not need any very complex equipment. We do not teach doctors how to work with potentiostat. We just give them electrode, we give them multimeter, and just ask, okay, connect 2 electrodes, and you got the number that is relevant to the concentration of your ions of interest. Now I need to step a little bit aside to explain how we synthesize and how we characterize MXene. This is very pretty standard procedure. We just modify it a bit to prevent oxidation of final MXene solution, because it's very crucial as MXene starts to lose its properties like conductivity, like ion selectivity, and so on. So we start with etching, then washing, delamination, and finally we finish with such dark green dense solutions. How we characterize MXene? We used a bunch of different methods. Here's PXRD, Raman, UVs, and DLS. And what is a good news that we have very nice quality MXene because you can see here there are plenty of reflections that related to MXene, and there is no presence any ML, a multi-layer phase or max phase. And based on Raman and UVs, especially those peaks and the absence of oxygen peaks here, so you can say that it's really MXene, not oxidized somehow MXene. And we are happy that mean size of our MXene was more than 1 micron, because during synthesis you really grind the MXene to the very fine powder, I would say. Yeah, of course we had to do XPS to prove that we do not have any presence of TO2, and the good stuff that we proved that we have only hydroxide and fluorine groups, terminal groups, with the ratio 1:1 roughly, and there is no, almost no chlorine. Microscopy tells us again that we have really big flakes. It's again very good for conductivity and so on, and that is really single layer MXene flakes. Okay, coming back to the electrodes, as I said, we have a kind of experience in polyelectrolytes layer and application of this layer to ion-sensitive electrodes. So here it's a very complicated procedure with which I had to work as well. And as a result of the complicated procedure, we oftenly got electrodes with leaking, with instability in behavior, and so on and so forth. And this is mainly due to the connection between ISE membrane and the isolation of the electrodes that were applied at the first stage. Okay, why not to change this polyelectrolyte layer? Well, first we of course add some MXene to these polyelectrolyte layers, but it didn't work. And then we said, okay, let's remove polyelectrolyte layer and leave only MXene. And finally we get some rigid design, fully isolated, very like maybe 90–95% of the electrodes working well. But we decided to go a bit further with simplification, and we just print, let's say we call it, use Dr. Blading procedure just to put some MXene material on the top of the glass, like this, and then make sensitive pads at the top, at the end of the electrode. And we could do it surprisingly on any substrate. It could be PVC, glass, paper, textile, whatever. We tried almost everything piece of flat surface that we can find in the lab. And also we could go for miniaturization. So you can see that very tiny electrodes can be done easily by hands. And let's say one electrode we have for, we call it a so-called a working electrode, and another like reference electrode, but well, they are both technically reference. Anyway, for one electrode we apply a membrane that contains this ionophore specifically for calcium, and another membrane was without this ionophore, so it was membrane without sensing capability. All the reagents are present here, and we need also ion exchanger because we need to maintain somehow the electroneutrality of the membrane. So, as we said, with this ionophore, one calcium ion in and two potassium ion out. Okay, we use, as I said, we can apply this to any plastic substrate, so we use this opportunity to study cross-section, and for cross-section you can clearly see that we have very tiny MXene layer, maybe micron or several microns, and we have very nice interaction between nail polish that we use to isolate the rest of MXene electrode and ion selective membrane. So what about the result? We tested our ion selective electrodes within solution, going from very low concentration to very high concentration. We obtain such nice linear slopes, and you can see that there is a cloudy stuff. It's error bars. Talking about limit of detections for those electrodes, for screen printed MXene electrodes, we achieve almost 2 orders of magnitude lower LODs if we compare them with what we started. And of course, we did batch tests. So, well, we can technically print it in batch, yeah, like very big and then cut. But we did it with more or less the same time, more or less the same MXene, more or less the same substrate. So there are 6 electrodes, and all 6 electrodes behave very, very, very similarly to each other. What about influence of external stimuli? Because we need to be sure that there is no interaction or interference with other ions like sodium and potassium, and especially magnesium, because magnesium is very similar in its properties to calcium ions. But as you can see here, it's very nicely done. And also, like, if we want to use it in any kind of environment, like medical environment, so we need to be sure that there is no interaction with UV light that can be used for sterilization, room light, and so on. So there is also no influence. We got kind of like stable signal. And finally, we tested all these electrodes with real-world samples, and here you can see San Pellegrino sparkling water. So when you buy it in your grocery, you are sure that now that the content of calcium is proper. Also, we used Black Sea water because we tested these electrodes at the border of Black Sea, and well, we haven't exact number how much calcium should be, but can you imagine seawater? You just put electrode inside and measure. So this is the mean result, and what we measured, I think it's good results. And finally, we tested it with milk. With milk, you have a lot of peptides, fatty acids, and so on and so forth. And with the milk, we also got pretty nice results. Well, when you start publishing, because in my application to this talk, I said, okay, we're going to publish very soon in small, but this is when you accept your manuscript, and this is when it's accepted. We had to wait for half a year before resubmission, but we head into small. So conclusions. I won't read what is written here, yeah, because I told more or less the same during my presentation. Only pointed out that we have very, very Nernst slope for our electrodes. So this is very, very nice. And we all, I think Michal, Andreas, and now me, from Hubert's lab, we all like to finish our talk with something, some wisdom. My wisdom for today is that everything should be done and made as simple as possible, but not simpler. And I think this is a good result, how you can eliminate unnecessary complications when you're working, for example, with ion selective electrodes. So about a little bit about future plans. We are going for MXene Sun, and probably related to previous talk, maybe it might be a solution for also batteries, because we can with such design and such sensor, I think we can make also progress with batteries, because here you can detect a lot simultaneously, a lot of ions and cations. That's all. I like to acknowledge and I'd like to thank all my team. Most of them, except Cartoscope, they are students or recently defended PhDs, and I would like to say thank ITMO Fellowship Program for financial support. So if you have any question, please, you can either ask me now, either during coffee break, or even send me some questions by Telegram. I hope I will answer it very shortly. Thank you very much.